You know, I was standing out my backyard last night, just doing the typical Tuesday stuff, taking out the recycling, and I just stopped to look up at the moon.
Oh, yeah. It was really bright last night.
Incredibly bright. It was a perfectly clear night, full moon, and I had this thought. If you think about it, it's really the most familiar thing in our lives, isn't it?
It is. It's the ultimate constant.
Right. It's the background wallpaper of being human. We write all this bad poetry about it. We track our months by it. It's this steady, romantic, completely silent presence. It honestly feels like a friend.
Yeah, the watchful eye. I think almost every ancient culture has some variation of that exact idea.
Exactly.
Yeah.
But then I started going through the massive stack of research you sent over for today's deep dive. And I have to say, this stack was significantly heavier than usual.
I might have gotten a little carried away with the source material this time.
No, it's great.
Yeah.
But I realized pretty quickly that my mental image of the moon, this quiet, static, silver rock in the sky, it's completely fictional. It is a lie we tell ourselves to feel safe.
It's a very comforting lie, but yeah, it's definitely a lie. When you actually strip away the mythology and the romance and you look at the sources, you start looking at the moon as a planetary mass object, which is what it technically is.
Right.
The reality of it is just so much more chaotic, it's violent, it's strange, and honestly, it's a little bit terrifying.
Terrifying is absolutely the right word. Because we are talking about a world born from a literal apocalypse, a world that is currently shrinking and cracking like a drying raisin.
Yep.
And this is the part that completely blew my mind in the notes. A world that apparently smells like gunpowder.
It does indeed smell like gunpowder.
Yeah.
And perhaps most unsettling of all, if you look at the orbital data, it's actually trying to leave us.
We are definitely going to get into that breakup story a bit later. But our mission for this deep dive is to construct a real biography of Earth's only natural satellite.
Right.
We're pulling from geological surveys, Apollo mission transcripts, some incredibly dense isotopic data, all to understand what this object actually is. And I think to really understand the moon, we have to start at the very beginning.
The origin story, which in the case of the moon is really a story about the single worst day in Earth's entire history.
The violent birth. Because the moon didn't just float by one day and get caught in Earth's gravity, right?
Mm-hmm.
I remember learning that in school, the old capture theory.
Right. The capture theory was super popular for a long time. It's this idea that the moon formed somewhere else entirely in the solar system, wandered past Earth, and just got snagged by our gravity, like a fly in a spider web.
Just passing by and got stuck.
Exactly. But the physics of that are just incredibly difficult to actually make work. You'd need to shed a massive amount of energy almost instantly to be captured smoothly like that.
Because it's moving so fast.
Yeah, it's mathematically highly improbable. If a body of that size came cruising by, it would likely either just swing past us and get slingshotted away, or it would crash straight into us. It wouldn't just magically settle into a nice, neat, circular orbit.
Okay, so if it wasn't a drive-by, what was it? Because the prevailing theory in the sources sounds like a pitch for a disaster movie.
It really does. The prevailing theory, and this is the one that fits almost all the physical evidence we've collected, is called the giant impact hypothesis. And when scientists say giant, I don't think people realize the scale we are actually talking about here. We mean cataclysmic.
So set the scene for us. We're going back, what, about 4.5 billion years?
Roughly 4.51 billion years,
Yeah.
So picture the early solar system. It is basically a demolition derby.
Just rocks everywhere.
Exactly. It's not the orderly clockwork system we have now where everything politely stays in its lane. There's debris everywhere. Protoplanets are just smashing into each other constantly. Earth is there, but it's the proto-Earth. It's incredibly hot, very volatile, and it's not alone in its orbit.
There's an intruder.
A second planetary body, roughly the size of Mars. Scientists have named it Theia, after the Greek titan who gave birth to the moon goddess Selene.
So we have Earth, and we have this Mars-sized planet, Theia. And they aren't just passing in the night.
Oh, no. Theia slams directly into the proto-Earth. And I really want to be clear about the sheer energy here. This wasn't a fender bender. This wasn't even an asteroid impact like the one that wiped out the dinosaurs.
Which was huge in itself.
Right. But this was a collision between two actual planets. The energy released was enough to completely liquefy the Earth's crust, and it absolutely obliterated Theia.
I'm trying to even visualize this. We're talking about a collision so violent that it turned solid rock into vapor.
Correct. It vaporized billions of tons of rock. It created this massive cloud of superheated dust and molten material. Some of that fell back to Earth, of course, but a huge amount of it was blasted out into orbit. It actually formed a ring around the Earth.
Wait, like Saturn?
very much like the rings of Saturn, but instead of ice, it was made of molten lava and vaporized silicate.
That is just an incredibly metal image. Earth with a glowing ring of lava.
It really is. And the heat was unimaginable. We are talking thousands of degrees. The atmosphere would have been stripped away entirely. Any surface oceans would have boiled off instantly if they even existed yet. It was a total reset button for the planet.
Oh.
But this is where the physics gets really interesting. This ring, this debris field, it formed just beyond what we call the Roche limit.
Okay, yes, let's unpack that term, because I saw Roche limit all over the source material. What does that actually mean in plain English?
So think of the Roche limit as a danger zone surrounding any planet. It's the minimum distance to which a satellite can approach its primary body without being torn apart by tidal forces.
Tidal forces mean gravity.
Yes, because gravity isn't totally uniform. If a moon gets too close to a planet, the gravity pulling on the front of the moon, the side facing the planet, is much, much stronger than the gravity pulling on the back of the moon.
So it's getting pulled unevenly.
Exactly. That difference in pull stretches the moon out. Inside the Roche limit, that stretching force is actually stronger than the moon's own internal gravity holding it together. So the moon just rips apart and becomes a ring of dust and rocks.
So if our moon had formed inside that limit, it would have just stayed a ring forever.
Precisely. We'd have a permanent ring system today. But this debris from Theia was pushed just outside that limit. Because it was outside the danger zone, gravity could safely do its work.
So it started clumping together.
Right. The clumps of magma and dust started sticking together, accreting, getting bigger and bigger, and surprisingly fast, too. Some of the newer simulations in the sources suggest the moon could have coalesced from that disk in less than 100 years.
Less than 100 years. That's a blink of an eye in geological time. Less than 100 years to build an entire moon.
It was a wildly violent, rapid accretion. And because of all the intense heat involved in that process, the infant moon wasn't a solid rock at all. It was a glowing ball of molten magma. The estimates say it had a literal magma ocean that was anywhere from 500 kilometers to over 1,700 kilometers deep.
A magma ocean 1,000 kilometers deep. Just imagining the view from Earth at that time, if you could stand there, looking up and seeing a giant glowing red orb instead of a white one. It must have taken up a huge portion of the sky too, right?
Oh, yeah. Been much closer to Earth than it is today. It would have dominated the sky. But this actually brings us to the biggest scientific puzzle in the notes you read. The chemical mystery.
Right, the isotopes.
Yeah.
This is where the real detective work comes in.
Yes. This is how planetary scientists do forensics. Every single object in the solar system has a totally unique chemical fingerprint based on where it originally formed. We look at isotopes, which are just variations of elements like oxygen.
So Mars has a specific fingerprint.
Exactly. Mars has its own specific oxygen isotope signature. Asteroids like Vesta have another. So logically, you would expect Theia, having formed somewhere else in the solar nebula, to have had its own distinct chemical fingerprint.
Okay, I follow you. So if the moon is made mostly of the wreckage of Theia, which the old computer simulations said it should be, the moon should look chemically different from Earth.
Exactly. It should look chemically like Theia, but it doesn't.
It looks like us.
It looks almost exactly like us. When scientists analyze the rocks brought back by the Apollo missions, the isotopic composition of the moon is nearly identical to Earth. It's like they are identical twins. And for decades, this completely broke the giant impact hypothesis. Scientists were just scratching their heads going, if a Mars-sized thing hit us, where is it? Why isn't the moon made out of it?
That is a massive plot hole for that theory. So how did the sources explain that now? Did Theia just not exist?
No, the physical models for the collision are too strong. We know something hit us. The leading explanation now is that the collision was even more violent than we previously thought. It was so insanely energetic that it caused a massive turbulent mixing of all that vaporized material.
Like a planetary blender.
A blender is the perfect analogy. It essentially homogenized Theia and the proto-Earth into a single mixed system. There's actually a specific term for this theoretical structure in the literature, a synestia.
Synestia. What does that look like?
Imagine a massive donut-shaped cloud of vaporized rock that is spinning so fast it flattens out. Earth and the moon both condensed out of this exact same cloud. They swapped so much material back and forth in that superheated vapor phase that their chemical fingerprints became identical.
Wow. That's oddly profound if you think about it. We aren't just partners in space, we're literally the same material. The moon isn't a stranger, it's a piece of us that got knocked off and reformed.
Or we are a piece of it. It's a shared heritage forged in absolute fire. We are two children of the exact same catastrophe.
That really changes how you look at it up there. It's a sibling. Okay, so moving the timeline forward, we have this cooling ball of magma. It eventually solidifies, the crust forms, and we get the moon we recognize today. But it doesn't just sit there. It starts this intricate dance with Earth.
Right.
And I want to talk about how we actually see the moon from down here. Because there is a phrase that appears in pop culture constantly, and the notes say it drives astronomers absolutely crazy, the dark side of the moon.
Look, it is a fantastic Pink Floyd album, truly one of the best. But it is a terrible astronomical term. There is absolutely no dark side in the sense of a place that is permanently in shadow.
But we only ever see one face, right? The man on the moon. I've never seen the back of his head.
That is true. We only ever see the near side. But the far side gets plenty of sunlight. Think about it. When we have a new moon here on Earth, when the moon looks completely dark to us, that means the far side is completely bathed in full sunlight.
Right, because the sun is hitting the back of it. So why do we only ever see the one face? Is it just blind luck? Did it just happen to stop spinning at the exact right moment?
No, it's not luck at all. It's physics again. It's a phenomenon called tidal locking.
How does that work?
So, think back to that infant molten moon. Earth's gravity is pulling on it constantly. Just as the moon pulls on our oceans today to make tides, Earth pulled on the moon's actual rock. It created a physical bulge in the moon's shape.
Like it stretched it out into an egg shape.
Slightly, yes. And Earth's massive gravity basically grabbed onto that bulge and acted like a brake.
A brake on its spinning.
Exactly. It created gravitational drag. Over millions of years, that drag steadily slowed down the moon's rotation. Eventually, it slowed down so much that its rotation period, the time it takes to spin exactly once on its axis, perfectly matched its orbital period around Earth.
So it spins at the exact same speed it orbits us.
Precisely. It takes about 27.3 days to orbit Earth, and it takes exactly 27.3 days to spin once on its own axis. The end result is that it always keeps the exact same face pointed at us. It's like, imagine walking around a campfire while making sure you keep your face pointed toward the fire the whole time.
You have to spin your body to do that.
Right. You have to turn to walk in a circle, but the fire only ever sees your face.
That is a brilliant analogy. And the far side looks totally different from our side, doesn't it? The sources mentioned that when the Soviets finally sent a probe around back there, the pictures were kind of shocking to scientists.
Oh, drastically different. The near side, the one we are used to seeing, is covered in those large dark patches we call maria, or seas.
Which aren't actually water.
No, they are ancient volcanic plains, huge flat basaltic lava flows. But the far side, it's almost completely devoid of those dark seas. It's heavily cratered, very rugged, what we call the highlands. It honestly looks like a completely different planet. It's much, much messier.
Why the big difference? Why did all the smooth volcanoes happen on our side?
Well, the current thinking is that the crust on the far side is significantly thicker. So back in the early solar system, when giant asteroids were hitting the far side, they couldn't punch deep enough through that thick crust to reach the molten mantle below and let the lava flow out.
Ah, okay.
But on the near side, where the crust was thinner, those massive impacts cracked it wide open like an eggshell, and it just filled those huge craters with dark lava.
That's fascinating. It really highlights how dynamic the whole system was.
Yeah.
Now, earlier you mentioned that the moon is, and this was a great phrase trying to leave us, the Great Drift.
Yes, this is one of those scientific facts that sounds like absolute science fiction, but
Well,
we literally measure it every single day.
How do we even measure that? I assume we aren't using a really long tape measure.
We actually use the Apollo legacy for this. The astronauts left these things called retroreflectors on the surface. They are basically incredibly high-tech mirrors.
All right.
Observatories here on Earth shoot high-powered lasers directly at those mirrors, and we meticulously time exactly how long it takes the light pulses to bounce back. That allows us to measure the distance to the moon down to a fraction of a centimeter.
That is some seriously precise shooting. And the verdict of all these lasers is?
The moon is moving away from Earth at a rate of about 38 millimeters per year.
38 millimeters. I think the notes said that's roughly the speed at which human fingernails grow.
That is the standard, slightly gross comparison we use, yeah. It sounds really small, doesn't it? But over deep geological time, it really adds up. When the moon first formed, we talked about how big it was in the sky. It might have been only 20 or 30,000 kilometers away.
And now?
Now it's nearly 400,000 kilometers away.
Wow. So what is pushing it away? Is it just losing momentum?
Actually, it's gravity again. Specifically, the ocean tides. So the moon pulls on Earth's oceans, right? It creates that tidal bulge, that high tide that travels around the planet every day. But here's the physics trick. Earth rotates much faster than the moon orbits us. A day here is 24 hours. The moon's orbit takes 27 days.
So Earth is spinning really fast underneath the moon.
Right. And because Earth is spinning so fast, the friction of the ocean floor actually drags that massive bulge of water slightly ahead of the moon's position in the sky. The high tide doesn't sit perfectly directly underneath the moon.
Okay, so the water is offset forward.
Yes, and that massive moving mountain of water has its own gravity. It physically pulls on the moon. Because that water bulge is ahead of the moon in its orbit, it constantly drags the moon forward. It gives it a tiny, constant gravitational kick.
Like pulling a dog on a leash.
Exactly. And the laws of orbital mechanics dictate that when you add forward energy to an orbiting object, it moves outward into a higher, larger orbit.
So our own oceans are basically shoving the moon away, inch by inch, like a slingshot that just never stops firing.
That's exactly it. And there is a real cost to that cosmic transaction. Physics says energy always has to be conserved. If the moon is gaining orbital energy and moving away, Earth must be losing energy from somewhere.
Losing it from where? Are we getting colder?
From our rotation. As we push the moon away, the friction of those tides sloshing around is acting as a brake on the Earth itself. Earth is slowly spinning down. Our days are actually getting longer by about 17 microseconds every single year.
Wait. So in the distant future, a day won't be 24 hours long.
Correct. And if you go backward to the time of the dinosaurs, a day was only roughly 23 hours long. Go all the way back to the early Earth, right after the moon formed, a day might have been only 6 hours long.
6 hours.
Yep. And in the distant future, days will be 25, 26, eventually 30 hours long.
That is such a wild thought. We think of a day as this fixed, immutable unit of time, but it's totally elastic. We're literally running out of time or gaining time, depending on how you want to look at it.
Everything in the solar system is constantly in motion. Nothing stays still.
But speaking of the tides, the sources mention it's not a one-way street, right? Because Earth is much, much bigger than the moon. I think the note said Earth is about 81 times more massive. So if the moon can pull our oceans, Earth must be doing something huge to the moon.
Oh, absolutely. We create massive tides on the moon, too. But since the moon has no oceans to slosh around, Earth's gravity creates what we call a solid body tide. We actually stretch the physical rock of the moon.
We stretch the rock.
We do. The moon's physical shape bulges by about 10 centimeters closer to Earth on the near side. It's like slowly squeezing a tennis ball.
The solid bedrock is moving 10 centimeters. That seems like an enormous amount of flex for stone.
It is a lot of stress. And here is the kicker. The moon's orbit isn't a perfect circle, it's elliptical. Sometimes it's closer to us at perigee, sometimes it's further away at apogee. That means the strength of Earth's gravitational squeeze is constantly changing. The moon is being constantly flexed, squeezed and released every single month.
And rock generally doesn't like to be flexed.
No, it's highly brittle. This internal friction and stress causes the lunar crust to crack and snap violently, which leads us to one of the most surprising discoveries of the entire Apollo era, moonquakes.
Moonquakes. I honestly just love that word. But they aren't like earthquakes, are they?
Not at all. On Earth, earthquakes are usually caused by massive tectonic plates grinding past each other. The moon doesn't have tectonic plates like we do. Its crust is one continuous shell. These moonquakes are caused by that tidal squeezing we just talked about, and also the slow cooling of the moon's interior. But the actual experience of feeling a moonquake would be wildly different from an earthquake.
How so? What would it feel like?
Well, if you have an earthquake in, say, California, the ground shakes violently, sure, but usually the seismic waves die down within a minute or two. Why? Because Earth is wet. The crust is totally saturated with oceans and groundwater, and the deep interior is hot and gooey magma. All that moisture and molten rock absorbs the seismic energy. It quickly dampens the vibration.
Like hitting a snare drum that's filled with water.
Exactly, just makes a dull thud. But the moon is incredibly dry, bone dry, and it's cold and rigid throughout most of its crust.
So what happens when that brittle rock quakes?
It rings like a bell.
Literally rings.
Literally. The Apollo astronauts left a network of seismometers up there. When they jettisoned their used lunar modules to crash back onto the surface, the impact of those crashes caused the moon to vibrate. The seismometers recorded the ground ringing for over an hour.
An hour. from one crash.
Yes. Imagine standing on the surface. A quake hits, and the ground creates this vibration that just builds and sustains for 60 straight minutes because the acoustic energy has absolutely nowhere to go. It just bounces around the fractured, dry crust endlessly.
That paints such a spooky, almost alien picture. You're standing on this dead, silent gray world, and suddenly the ground starts vibrating under your boots and just won't stop.
It would be terrifying.
And speaking of being on the surface, let's dive into what it's actually like down there. Because the source material goes into some really gritty detail about the surface environment.
It does. We tend to casually think of the moon as a perfect vacuum. And for all practical, everyday engineering purposes, it really is. The atmospheric pressure is about 10 to the power of -7 pascals. That's effectively 0. But technically speaking, it actually has an atmosphere.
An atmosphere. Wait, I thought if you took your helmet off up there, you'd basically explode.
Well, you certainly would not survive it, no. But there's a very, very thin layer of gas clinging to the surface called an exosphere. It's so vanishingly thin that the individual atoms rarely ever even bump into each other. But it's there. It contains traces of helium, neon, argon, and oddly enough, sodium.
Sodium? Like table salt?
Yes, elemental sodium. In fact, if you use the right specialized filters on a powerful telescope, you can actually see that the moon has a faint sodium tail streaming behind it, blown outward by the solar wind. It looks almost exactly like a comet.
That is completely bizarre. Our moon has a comet tail made of salt. But honestly, the thing that really stood out to me in the notes and the thing that seems to keep the NASA engineers up at night is the dust, the regolith.
Oh, regolith is the absolute enemy. It is arguably the single biggest engineering challenge for any future lunar exploration.
I was just thought of it as sand. You look at the old footage of the Apollo astronauts bouncing around, kicking it up. It just looks like a gray beach. But it's not sand at all, is it?
It is the complete geological opposite of beach sand. Think about how sand is formed here on Earth. It's rock that has been tumbled by ocean waves, blown around by wind, ground down by river currents. Over millions of years, those erosive processes round off all the sharp edges. Sand grains are basically tiny, smooth little pebbles.
Okay, that makes sense.
But the moon has no wind, no water, no rivers, no weather of any kind. The dust on the moon is formed by one thing and one thing only: extreme violence. Meteor impacts.
This rock smashing rock.
Exactly. High-velocity micrometeorite impacts shatter the surface rock into microscopic fragments. But because nothing ever tumbles them or smooths them out over time, they never lose their edges.
So they are.
They are microscopic shards. Every single individual grain of moon dust is a tiny shard of glass with razor-sharp, jagged edges.
Oh, wow. And the note said it sticks to literally everything.
Everything. Because it's heavily electrostatically charged by the constant solar radiation bombarding the surface, it acts exactly like static cling or Velcro. The Apollo astronauts couldn't brush it off. It coated their pristine white spacesuits until they looked like they'd been working in a coal mine. It instantly clogged the joints and seals of their tools. It severely scratched their helmet visors. It actually started wearing through the outer layers of their Kevlar boots.
That is wild. It's essentially an abrasive magnetic powder that destroys everything it touches. But the most interesting part, and honestly the most eerie part, is what happened when they finally got back inside the lunar module and took off those helmets.
The smell.
The smell. Harrison Schmitt, who was the geologist on Apollo 17, and several other astronauts reported a very distinct odor immediately filling the cabin. They said the moon smelled strongly of spent gunpowder.
Yeah, the Apollo aroma.
But why would moon dust smell like gunpowder? Is there some kind of explosive material just lying around up there?
No, not at all. And that's the really fascinating chemical puzzle of it. The regolith, obviously, isn't made of gunpowder, which is a mix of sulfur, charcoal, and saltpeter. The leading scientific theory right now is that the smell is actually a rapid chemical reaction happening right there with the astronauts' own environment.
How does that work?
So for billions of years, that pulverized dust has just been sitting out there in a hard vacuum, being relentlessly bombarded by the solar wind. This solar wind implants hydrogen and helium directly into the crystal structure of the rock. But more importantly, the radiation actually breaks the chemical bonds on the surface of the dust grains. We call these broken links dangling bonds. They are chemically desperate to connect with something, anything.
They're chemically lonely.
Extremely lonely, highly reactive. So the astronauts track all this hyperreactive dust into the lunar module on their suits. They seal the door and repressurize the cabin with breathable oxygen. Suddenly, for the first time in perhaps billions of years, that dust meets pure oxygen and water vapor from the astronauts' breath.
So it was a chemical reaction happening right inside their noses.
Exactly. Those unsatisfied, dangling chemical bonds reacted instantly. They oxidized with the moisture and atmosphere in the cabin. That rapid oxidation process creates a smell that the human brain interprets as the sharp, burning smell of spent gunpowder. It's a smell that technically doesn't even exist out on the moon itself. It only exists in that fleeting moment of transition from a dead vacuum to a living atmosphere.
That is incredibly cool. It's literally the smell of space reacting as it hits the air.
Yeah.
But also, this dust sounds seriously dangerous. If it's made of sharp glass shards, breathing that in cannot be good for you.
It is a massive health hazard. If you inhale it, it can cause severe respiratory issues very similar to silicosis or coal miners' pneumoconiosis. Those microscopic sharp edges can literally shred the delicate alveoli inside your lungs. If we are ever going to live there permanently, we have to definitively solve the dust problem first.
So note to all future space tourists listening, do not snort the moon dust.
Generally solid advice for any celestial body you visit, yes.
Right. Now, we talked about the moon ringing like a bell earlier, but the surface itself is actively changing too. The notes mention that the moon is actually shrinking.
Yes, it is. We used to think the moon was totally geologically dead, just a cold fossil. But it's surprisingly active. As the deep interior of the moon slowly cools down over billions of years, it naturally contracts. It's just simple thermodynamics. Things shrink when they lose heat.
But the crust is hard, solid rock. It can't just shrink smoothly like a balloon deflating.
Exactly. The hot core shrinks, but the cold outer crust is brittle, so it has to somehow accommodate that smaller surface area underneath it. It buckles, it cracks.
Yeah.
It physically thrusts one massive section of crust up and over another section.
A grape turning into a raisin.
That is the classic geological analogy, yeah. The moon is literally wrinkling. This global shrinking process has created these massive, steep cliffs all over the surface called fault scarps. Some of them are dozens of meters high and extend for many kilometers across the landscape. And the crazy thing is, this isn't ancient history. This is happening right now. We strongly suspect that some of those shallow moonquakes the Apollo sensors picked up are actually the sound of the moon actively shrinking, the crust suddenly snapping and thrusting as it contracts.
It's shrunk by about 90 meters in the last billion years, right?
Roughly that radius, yes. It's a very slow, continuous squeeze.
It's just amazing to think of it as this dynamic, shifting thing in the sky. And speaking of dynamic, let's talk about volcanoes, because I definitely thought the moon was completely done with volcanoes billions of years ago.
For a very long time, so did the entire scientific community. We thought almost all major volcanism ended way over 1 billion years ago. The big dark seas, the Maria, those lava flows are roughly 3 billion years old. But recently, the Lunar Reconnaissance Orbiter found these very strange small features scattered around called irregular mare patches.
The sources called them IMPs.
IMPs, right. There's a very famous one at a location called Ina. These features look remarkably confusingly fresh. They don't have very many impact craters on them at all. And in planetary astronomy, crater counting is basically how we tell time. Lots of craters means the surface has been sitting there a long time. Few craters means it's relatively young because it simply hasn't had time to get hit by space debris yet.
So how young are these IMP patches?
Some of the estimates in the literature suggest they could be as young as 50 million years old.
50 million. I mean, in geologic time, that's basically last week. The dinosaurs were already completely gone by then. Mammals were walking around on Earth.
Exactly. It implies that the deep interior of the moon stayed hot enough to produce actual volcanic eruptions much longer than any of our thermal models said was physically possible. It challenges our fundamental understanding of how small planetary bodies cool down over time. The moon might actually still be warm and mushy on the very inside today.
Okay, so we've got shrinking crusts, gunpowder-scented dust, surprisingly recent volcanoes. But the biggest game changer for me in all this research and for the future of humans ever going back up there is the water.
Oh, this has been the biggest paradigm shift in lunar science in the last 2 decades, hands down. We used to think the moon was absolutely uniformly bone dry, just desiccated rock.
And now?
Now we know water is definitely there, and it exists in a few completely different forms. The most famous and abundant cache is located at the poles.
The cold traps.
Yes. So the moon has almost zero axial tilt relative to the sun. Because of that, if you are at the true north or south pole, the sun is always just skimming right on the horizon. It never gets high overhead. Therefore, if you have a very deep crater at the pole, the bottom floor of that crater never, ever sees sunlight. Not for a million years, not for a billion years.
Eternal darkness.
Eternal darkness and eternal cold. These permanently shadowed regions, PSRs, are literally some of the coldest places measured in the entire solar system. They are often colder than the surface of Pluto. So, if an icy comet hits the moon somewhere and releases a plume of water vapor, those water molecules will hop around the surface in the exosphere. If they land in the sunlight, they instantly burn off and escape into space. But if they happen to hop into one of those dark polar craters,
Freeze out.
instantly, and they can never leave. They're thermally trapped forever. We now believe that billions of tons of water ice have slowly accumulated in those craters over the eons.
So there are just potential massive ice rinks hiding at the poles. But the notes also mentioned something else that sounded crazy: glass beads.
Yeah, this is a much more recent and very subtle discovery from the lunar soil samples. Scientists found tiny amounts of water trapped entirely inside microscopic glass beads in the regolith. These beads are formed by those violent meteorite impacts we talked about. When a rock hits at thousands of miles an hour, it instantly flash melts the surface rock into glass, and sometimes it physically traps tiny amounts of ambient water inside the glass sphere as it rapidly cools.
And then there's Sophia. The notes Sophia actually found water on the sunlit surface too, right?
Correct. The Stratospheric Observatory for Infrared Astronomy, which was basically a giant telescope strapped into the side of a modified Boeing 747, it actually detected the distinct spectral signature of molecular water, H2O, right on the sunlit side of the moon.
Wait, how is that possible? You just said sunlight boils the water off instantly.
It does, so it's definitely not sitting there in puddles or frost. It's highly likely that these are individual water molecules chemically bound to the actual mineral grains in the dirt, or perhaps trapped inside that impact glass we just mentioned. The rock essentially holds tightly onto the water molecule, shielding it from the hard vacuum and the extreme heat. But the implication is huge. It means water is much more ubiquitous across the moon than we ever thought. It's not just isolated at the poles, it's basically everywhere, just in very, very tiny, difficult-to-extract amounts.
Which transitions us perfectly into the human part of this story.
Yeah.
Because if there is water up there, that changes absolutely everything for space exploration. We aren't just going there to plant flags and look at rocks anymore. We're going there to stay.
Water is the absolute oil of the modern space age. It is the heavy lifter for everything. Obviously, you can drink it, sure. But much more importantly, you can use solar electricity to split that water into oxygen for breathing and hydrogen for rocket fuel.
It's a gas station.
It is a literal gas station in the sky. If the moon has accessible water that we can mine, we don't have to drag all our insanely heavy rocket fuel up from the bottom of Earth's deep gravity well. We can just launch empty, gas up on the moon, and fly onward to Mars or beyond. It fundamentally changes the economics of all space travel.
So let's look at the history of humans actually going there. Because it started out as a massive race, the space race.
Pure Cold War geopolitics. It was a technological proxy war between the US and the Soviet Union. And I feel like people often forget that the Soviets were actually the very first to reach the moon.
Luna 2.
1959. Luna 2 didn't land softly. It intentionally impacted the surface. But it was the very first human-made object to ever touch another celestial world. That was a massive geopolitical statement at the time.
And then Luna 3 right after.
Luna 3 swung around and took the very first pictures of the far side, also in 1959. That was a huge reveal for science. Humanity had literally never seen that face of the moon before. Can you imagine being the first scientist in that dark room to develop those grainy photos and see rugged highlands and craters where you fully expected to see smooth, dark seas?
It must have been incredible. And then, of course, the Americans caught up and surpassed them. Apollo 8 orbiting in '68, which famously gave us that breathtaking Earthrise photo, and then Apollo 11 actually landing in '69.
Right. From 1969 to 1972, 12 men walked on the surface. They did geology. They set up instruments. They even drove cars, the lunar rovers, around on the surface. And then complete silence. For decades, we simply didn't go back, at least not with human beings.
But the robots definitely kept going.
Yeah.
And recently, looking at the sources, the player list has expanded quite a bit. It's not just a superpower duopoly of the US and Russia anymore.
No, it is a very crowded field up there now. China has been incredibly successful with their lunar program. Their Chang'e 4 mission was the first spacecraft ever to land softly on the far side.
Why is landing on the far side so much harder?
It's purely a communication issue. If your robot is on the far side, the entire mass of the moon is physically blocking your view of Earth. You cannot send a radio signal through 3,000 kilometers of solid rock. So China had to first launch a specialized relay satellite named Quekio into a halo orbit around a point way out behind the moon just to bounce radio signals back and forth to the lander.
That's incredibly complex. And India's there too now.
Yes, India's Chandrayaan-3 landed incredibly successfully near the South Pole region just recently. That is absolute prime real estate right now because of that polar water ice we talked about. Every space agency wants to be near the poles now. And Japan also recently joined the club with their SLIM lander, which actually managed to survive the brutal lunar night, which is 2 full weeks of freezing absolute darkness, despite not even really being designed with the heaters to do so.
Wow. Now that brings up a really weird story from the source material. You called it the tardigrade affair. This sounds exactly like a sci-fi B-movie plot, but it genuinely happened.
It did happen, and it raises some very serious ethical questions for the future. So in 2019, a private Israeli mission called Bereshit attempted a soft landing. Unfortunately, the engine failed and it crashed hard into the surface. The lander was carrying a cultural library, basically human knowledge etched onto incredibly durable nickel discs. But without telling many people, someone on the team decided to also secretly include thousands of dehydrated tardigrades in the payload.
Water bears, those microscopic little extremophile animals that are basically indestructible.
Yes, tardigrades are legendary extremophiles. They can survive the vacuum of deep space, they can survive extreme ionizing radiation, and they can survive near absolute zero temperatures. So when that lander crashed and shattered, those thousands of tardigrades were violently scattered straight onto the lunar regolith.
Are you telling me there are microscopic bears living on the moon right now?
Well, technically yes, but in a dormant state. They are highly likely in what biologists call a ton state. They are completely dried out, curled up, and metabolically inactive. They definitely cannot move, eat, or reproduce without liquid water. But the incident sparked a massive, angry debate in the space community about planetary protection.
Did we just irreversibly contaminate a pristine celestial body?
Exactly. Did we violate the ultimate leave no trace rule of the solar system? Now, the moon has a fairly low planetary protection category because we are 99.9% sure it doesn't have any native life of its own to disrupt. But as we look ahead to landing on Mars, or Jupiter's moon, Europa places, that very well might have alien microbial life, this precedent becomes highly critical. We absolutely do not want to spend billions of dollars to discover life on Mars, only to realize a year later that it's just Earth bacteria we accidentally brought with us on the rover's landing gear. Oh, that would be tragic. And that naturally leads into the big legal question in the notes. Who actually owns the moon? If I build a rocket and land there tomorrow, can I just claim a crater for myself? Can I stick a flag in the dirt and say, I declare this New Jersey?
According to the Outer Space Treaty of 1967, which is essentially the foundational constitution of all international space law, the answer to that is a hard no. No nation, and by extension no private citizen, can claim national sovereignty over the moon or any other celestial body. It is legally defined as the province of all mankind.
Okay, so no planting flags for legal ownership of the dirt. But what about the resources? If I spend billions to set up a mine and dig up that polar ice, do I own the ice I extract?
That is the massive, highly contentious gray area we are currently fighting over diplomatically. The U.S. and several partner nations have recently drafted and signed something called the Artemis Accords. Their legal interpretation of the treaty is basically, you cannot own the land itself, but you absolutely can extract, own, and sell the resources you pull out of it.
It's like fishing in international waters. That is the exact analogy space lawyers use. You don't own the Atlantic Ocean, but if you put a net down and catch a tuna, you legally own that tuna.
I can easily see how that interpretation would cause international tension. I mean, if there is really only one perfectly placed crater at the South Pole, with easy, shallow water access and constant sunlight on the rim, and the U.S. or a U.S. company sets up a huge mining rig right there, they effectively own that crater, even if they explicitly say they don't own the land.
Precisely. The Artemis Accords allow for the creation of safety zones around equipment where other nations' rovers can't interfere to prevent accidents. But critics argue that's just de facto territorial ownership by another name. And definitely not everyone agrees with this framework. There is actually a fascinating counter-movement, which was mentioned in your sources, called the Declaration of the Rights of the Moon.
Yeah, please tell me about that. Because it sounds like it treats the moon like it's a living person.
Essentially, yes. It proposes legally granting the moon a legal personality. Now, this isn't entirely unprecedented in Earth law. Several rivers, like the Wanganui River in New Zealand and the Ganges in India, have recently been granted legal rights by courts. The core idea is to protect the entity from reckless exploitation, to legally view the moon as a commons that has an inherent right to exist unchanged and unpolluted, rather than just viewing it as a dead warehouse of resources waiting for humans to plunder.
That is a really fascinating shift in perspective. Instead of immediately asking what can we take from it, it's asking what right do we have to permanently scar this ancient, pristine world.
Right. It connects very deeply to the broader environmental movements here on Earth. If we culturally treat the moon as just dead rock, we will inevitably strip mine it. We will pollute the exosphere. We will scar the surface. If we treat it as a sovereign entity with inherent rights, we might be forced to tread much more carefully.
And we really do have a deep, ancient connection to it as a species.
Yeah.
I mean, the sources dive into this heavily in segment 5, the human connection. We have been watching the moon for literally as long as we have been human.
Absolutely. The oldest potential data processing devices we have ever found in the archaeological record, these carved tally sticks from 30,000 years ago, like the famous Lobombo bone, they strongly appear to be early humans carefully tracking lunar phases.
So before we even had written language, we had the moon.
We organized our entire survival around it. The very word moon comes from a Proto-Indo-European root, which literally means to measure. The entire concept of the month is a lunar construct, mensis in Latin. It was our very first clock and our very first calendar in the sky.
But then, of course, there's the darker side of that psychological connection, the lunar effect, this pervasive idea that the full moon literally makes people go crazy. Lunacy. Lunatic.
It is so deeply embedded in our global culture. If you ask almost any police officer or emergency room nurse, they will swear to you on their lives that things get noticeably wilder and more violent during a full moon. They all say it. It must be a full moon tonight.
But the research in the notes says
The hard science is absolutely no. Over 37 massive peer-reviewed studies have looked at this comprehensively. They've tracked crime rates, hospital admissions, traffic accidents, severe psychiatric episodes, even dog bites, you name it. There is absolutely zero statistical correlation between human behavior and the full moon.
So if the data is zero, why does everyone so fiercely believe it?
It's a textbook case of confirmation bias. If a really crazy, chaotic night happens to land on a full moon, you look up, you notice the giant bright moon, and your brain says, aha, that perfectly explains it, and you remember that association forever. But if an equally crazy night happens on a dark new moon, you just think, man, people are acting crazy tonight, and you completely forget about it by next week.
But I've heard people argue the physics of it. They say, look, the moon is powerful enough to move the entire ocean. Humans are made of mostly water. So if it can pull the ocean, it must be subtly pulling the water in my brain, right?
I hear that all the time, but that is a fundamental misunderstanding of how gravity and tides actually work in physics. Tides only work because oceans are incredibly massive. They are planet-sized bodies of liquid. The gravitational difference across the massive thousands of miles width of the Pacific Ocean is significant enough to cause a bulge. But the gravitational difference across the 6-inch width of the human brain, it's mathematically non-existent.
So the actual tidal pull on my body is weak.
A mosquito landing on your arm exerts more physical gravitational pull on your body than the moon does from 400,000 kilometers away.
Wow. Okay, so I'm sorry to all the werewolves listening, but the science is definitely not on your side.
I'm afraid not. The moon undoubtedly affects our hearts and our culture through poetry and light, but it definitely does not affect our brains through gravity.
So let's look forward to the future before we wrap up. We talked a bit about the Artemis program. We are actively going back. But the notes mention using lava tubes as actual shelters. Is this how we are going to survive living there?
This is genuinely the most practical and elegant solution for long-term lunar habitation. The surface of the moon, as we've established, is incredibly harsh. The radiation levels are deadly because there is no magnetic field to deflect the solar wind. Micrometeorites are constantly raining down, and the thermal temperature swings are brutal. It goes from boiling hot, like 120 degrees Celsius during the day, to freezing cold, minus 130 degrees Celsius at night every 2 weeks.
That is just terribly hard on equipment, let alone biological people.
But lunar orbiters have discovered these amazing things called skylights. They're basically collapsed holes in the ground that lead down into vast, empty underground tunnels. These tunnels were carved out billions of years ago by ancient, flowing lava rivers. They are essentially pre-built subway tunnels, some of them kilometers long and hundreds of meters wide.
Literal pre-built moon bases just waiting for us.
Essentially, yes. The environment down inside those caves is perfectly stable. The temperature hovers constantly around 17 degrees Celsius, which is about 63 degrees Fahrenheit.
Wait, really? That's just light sweater weather. That's totally comfortable.
It is remarkably mild. The thick basalt rock ceiling completely protects you from all the cosmic radiation, it physically shields you from meteorite impacts, and it keeps the temperature perfectly steady year-round. So if we are going to establish a permanent presence on the moon, we almost certainly won't be living on the surface in fragile glass domes like you see in the sci-fi movies. We will very likely be living deep underground, safely tucked inside the moon itself.
Becoming cave dwellers again, just to become a spacefaring species.
Yeah.
There's a really beautiful poetry to that cycle.
It closes the human loop very nicely, doesn't it?
It really does. So, just to recap our whole mission today, we've stripped away the gentle romance, and we found a world that was violently born from a massive collision with the planet Theia.
A world with a global magma ocean that eventually cooled into a brittle crust that is right now actively shrinking and quaking.
A world covered in razor-sharp glass dust that mysteriously smells like gunpowder when it hits oxygen.
And a world that is slowly, millimeter by millimeter, drifting further away from us, making our Earth days just a tiny fraction of a second longer every year.
It's definitely not just a dead rock hanging in the sky. It's a completely dynamic, evolving partner in this long planetary dance.
And I think it reminds us that absolutely nothing in the universe is truly static. Even the things that look the most eternal, like that steady moon in the night sky, are constantly changing. They have violently chaotic past and a slowly drifting future.
Well, here's a final provocative thought I want to leave everyone with. Something for you to chew on after the deep dive is over. We talked very briefly about how the moon stabilizes Earth's tilt. I really don't think we emphasize that enough. The moon's gravity actually acts like a massive gyroscopic stabilizer on a ship, keeping Earth's rotational axis perfectly steady at 23.5 degrees. That specific tilt is what gives us our mild, predictable seasons. It makes our global climate stable enough for complex life to have evolved over millions of years.
It's vital. Without the moon's heavy anchor, Earth might wobble wildly and chaotically on its axis, much like Mars currently does. Our climate would swing between uninhabitable extremes.
Right. But we know for a fact it's drifting away from us, 38 millimeters a year.
Yeah.
So in the very, very distant future, as it moves much further out into space, its gravitational grip on our tilt will inevitably weaken. Earth could eventually start to wobble. The beautiful seasonal climate stability we completely rely on is ultimately a temporary gift.
It is a finite window.
So tonight, as you take out the recycling, or if you just look up at the night sky, maybe we should all say a little thank you to our violent, shrinking, gunpowder-smelling friend up there. Because without it, we quite literally wouldn't even be here to look back at it.
A very sobering thought.
Thanks for diving deep with us today. We'll see you on the next one.
Keep looking up.